Welcome back. We are going to look at the second half of section 2.6. We've been discussing families of functions and how to translate them. Our focus today will be on the stretching and compressing. There is a horizontal stretch and compression, but we're going to focus this year on the vertical ones. And as you continue on in your math classes, you will learn about the horizontal stretches. So a vertical stretch is basically taking your shape and pulling it in both directions vertically. So think of a rubber band that you're stretching. Your x values are going to stay the same, but your y values get increased. They get multiplied by a factor bigger than 1. So whenever you're doing a vertical stretch, there's going to be a number in the front of your function, and if it's greater than 1, it's going to pull your graph and make it taller. So for example, if we started with our blue graph and we stretched it, our red would be a vertical stretch. Okay, so instead of being here, we've pulled it up to here. Instead of being here, we've pulled it to there. So we're just making it taller in both directions. A compression is going to do the opposite. It's going to squish it down. So that's the green graph that you're seeing. We're taking all of our values, our y values, and compressing them down. So a vertical compression, again, your x values are going to stay the same, but we're going to change our y values and make them smaller. So the number that you see in front here is going to be something between 0 and 1. Like a 1/2 or a 1/3 or 3/4. Anything between 0 and 1 is going to compress it. So to graph a stretch or compression, we're still going to start out by making a table of the parent function. We always start with our parent function. Then we're going to add another column to that parent function table to get our new y values, and we'll graph those. So let's start by just looking at our parent function, y equals x squared. Hopefully by now you're kind of visualizing that that's a parabola. Let's go ahead and start with our normal -2 to 2 values. And if we're just going to look at y being x squared, we're squaring each of those. -2 squared becomes 4, -1 squared becomes 1, 0 squared is 0, 1 squared is 1, and 2 squared is 4. But now we want to change this. We want to put a 1/2 in front. So it's going to take all our y values and compress them to half their size. Okay, so if we want 1/2 of our x squared, we need half of 4. We need half of 1. Half of 0 is still 0. Half of 1, half of 4. So we are going to graph these x's, but paired with these new y values. Okay, so our first ordered pair, let's actually start with our parent function. Let's go ahead and graph that. -2, 4, -1, 1, 0, 0, 1, 1, and 2, 4. Okay, now if we're going to compress these, so our purple dots, we have a vertical compression of 1/2. We've made everything get half as tall. So instead of being up here at 4, we're going to shift those 2 dots down to 2's. Okay, half of 1 would be 1/2. Half of 0 is still 0. So my graph ends up looking a little squashed compared to the parent function, which would have been this one. Okay, so we've just squashed it down a little bit. For this one, because our a value here is bigger than 1, we are going to have a vertical stretch. Okay, so again, we're going to start with our parent function. Our parent function, we've already calculated these points. Squaring, we're just basic x squared graph. But this time we want our new y values to be twice that. Okay, so whatever we had for our old y value, this 4, is now going to become an 8. 1 gets doubled. 2 times 0 is still 0. 2 times 1, and 2 times 4. So now for those same x values, 0, 0, negative 1, 2, positive 1, 2, negative 2, 8, and positive 2, 8. So now you can see that our graph is getting skinnier. We're pulling that up. Okay? All right, let's look at putting all of this together. It says write an equation that's going to stretch the parent function, y equals the square root of x, by a factor of 2. Okay, so we want a vertical stretch of 2. We want it to translate 7 units to the left, and we want it to move down 2. Okay, so let's go through and look at our steps. To do a vertical stretch of 2, we need to put a 2 in front of our function. Okay, so our vertical stretch here will cause a 2 to move there. If we want to shift it to the left 7, we need to have a plus 7 inside our function. So it has to be inside that square root symbol. And then the last part, to get the down 2, any movements up and down are on the outside of your function. So outside of our square root, we would need a negative 2. Okay, write an equation that compresses the parent function. So we're compressing our parent function, y equals x cubed, by a factor of 1/3. Then we're going to translate it 3 units to the right. And then we're going to shift it 1 space up. Okay, so let's look at our parent function. We started out with y equals x cubed. Notice I left a little space there because we're going to add some numbers in here. If we want to compress the parent function by a factor of 1/3, then we need to have a 1/3 in front of our function. If we're going to translate it 3 units to the right, we're actually going to have x minus 3. That negative sign, if you want to think of it as kind of being built into your equation, and then put your 3 in as you move right 3. And then to shift it 1 unit up, on the outside at the end here, we would want a plus 1. Describe the transformation of the parent function y equals the absolute value of x for this new one. So again, we're going to walk through in order as we see numbers. So the first thing I see is this 3. Okay? Since my 3 had a value, and I'll just put here y equals a times some function x minus h plus k. And that function can be an absolute value, a square root, a cube root, cubes, whatever. But your x minus h piece is going to be inside some kind of function. Because this a value is bigger than 1, we know we have a vertical stretch by a factor of 3. Looking inside, an x minus 1, remember it shifts opposite of the way when you see a negative, it's actually moving to the right. So we are going to go right 1 space. And then our numbers on the outside move up and down in the same direction it looks like it should move. So a plus 2 is going to go up 2 spaces. All right, our last question here. The graph of y equals 4x is compressed vertically by a factor of 1/2, and then it's reflected over the y-axis. What is the new function rule? So let's start with our compression. We have the equation y equals 4x. If we want to compress it, that means we have to put the 1/2 in front of our function. And that would turn that into just a 2x. We've shrunk it down to half its size. Then we're going to reflect it over the y-axis. Remember that reflections change the opposite variable. So if we're reflecting over the y-axis, taking a point here and reflecting it over to there, it's the x value that changes. So we're going to have to change our x value. So instead of x, we're going to have the opposite of it, which gives me the new equation y equals negative 2x. That would be compressed and then reflected over the y-axis. All right, let's try one more. You can add this one to your notes. If I gave you y equals negative 1/3 times x minus 2 to the second power minus 7. Okay, let's look at our transformations. Now, the negative in front, you need to think of as separate from the 1/3. That negative causes a reflection, and because it's on the outside, we're changing all of our y values to the opposite of what they were. So we are reflecting over the x-axis. Our next piece is the 1/3. That is our a value. And because it's in between 0 and 1, it's going to be a vertical compression of 1/3. Okay, then we have the minus 2 inside. And remember, inside the function, inside with x, is going to shift things left and right. It's opposite of what we think, so we see a minus 2, we're actually moving to the right 2. And then any shifts on the outside move up and down. Because it's negative, we're moving down 7. All right, go ahead and practice putting all of these different transformations together.